All right, so page 2, we start with number 4. We're going to have a not continuous function, not differentiable function, and if you remember in class, I told you to write at x equal to 1. So at x equal to 1, I'm already telling you the function is not continuous and not differentiable, and you're just going through the steps of proving it. So for part A, I'm going to do the 3-step proof using the definition of continuity. I'm going to set myself up first. All right, so definition of continuity says that the limit as x goes to that value we're checking on 1 of the function is going to be equal to f of 1, the y value. The problem is we know it's not continuous, so this won't be true. So the limit, to find the limit, you're going to do the left side limit, which is the limit as x goes to 1 from the left. You're going to do the right side limit, which is the limit as x goes to 1 from the right. And then you're going to do the y value, which is f of 1. So let's start out with f of 1 because that is going to be very specific. You're always going to look for that equal sign. So because the equal sign is on the bottom function, to evaluate f of 1, I'm going to have to use the x squared plus x minus 2, which gives us 0. I know that when I want to do the left side, that would be this side, and this would be the right. So the left-sided function, the limit would be 3 times, 3 times 1, and then minus 1, which equals 2. The right side would be 1 squared plus 1 minus 2, which we already figured out was 0. Since these are not equal, we know that the limit is not going to exist. So the limit as x goes to 1 of f of x does not exist. But f of 1 is 0. So the statement is not all true, which means it's not continuous at 1. To be continuous, each of these 3 things have to be the same value. Moving on, you get that it's not continuous, not differentiable. Show one-sided derivatives using the difference quotient. And before we do that, remember off to the side here, I actually found the derivative using rules. And the rules would say that f times of 1 would be, take the derivative of 3x minus 1, and that's 3. Take the derivative of x squared plus x minus 2, and that's 2x plus 1. But I'm going to substitute in 1 and get 3. So it looks as though the derivative exists, but we know it doesn't because it wasn't continuous at 1. Now I'm going to show you that when you use the difference quotient, it is very evident that the derivative doesn't exist at x equal to 1. Alright, so I want you to notice that here, this and this makes it seem like the derivative exists. We already know it doesn't exist because the function was not continuous. So I'm going to go through and we're going to find the limit as h goes to 0 from the left. So if I'm using the left side function, that would be this one, 3 times x, which is now 1 plus h, minus 1, all over h. In this case, I would have the limit as h goes to 0 from the right, and the f of 1 plus h function would be this guy here, which is the right function. So 1 squared, 1 plus h, whole thing squared, plus 1 plus h, minus 2, all over h. And then remember, I'm subtracting away f of 1. Well, f of 1 we already found. If you remember, f of 1 was equal to 0. So, if f of 1 is 0, it's the same y value here and here. So the difference is, and I'm going to highlight it in green, the difference is this piece right here. That's what gave us this in red, and that's what gave us this in red. And that's the part that's actually different when you do one-sided derivatives. Now I'm just going to take the time to simplify this guy. I'm coming down here with my pen in pink. Limit as h goes to 0 from the left-hand side would be 3 times 1 is 3. 3 times h is 3h minus 1 all over h. And you get that the limit as h goes to 0 of 3h plus 2 over h. But if you remember in class, we said there's no mistake. I know I did everything right. the h's will not cancel, so the derivative can't exist as h goes to 0 because it would give me an undefined on the bottom. So there's our left side derivative. On the right side, down below, this is going to take a little bit of extra work here because remember I'm going to square this piece. So I actually get the limit, see if I can fit it here, as h goes to 0 from the right would be 1 plus 2h plus h squared. And then I would have plus 1 plus h. So I actually get h minus 1. And I get the minus 1 from using the 1 minus the 2. And then that whole thing is over h. Now, in orange, the right-sided derivative would be the limit as h goes to 0 from the right of, so everything's being added. There's no negatives anywhere. So I'm going to do h squared plus 3h all over h. Let me make sure I did that correctly. I'm going to factor out an h, and I get h plus 3 all over h. Those cancel. Now that it's completely simplified, I can put 0 in, and actually, let me change the color there to pink. And so I actually get 3. 3 does not equal the left-sided limit, which does not exist. Therefore, that's the 3 dots, therefore f primed of 1 does not exist. Those are not the same value. The limit of the derivative from the left and the derivative from the right are not the same value. So, y is, in part C, the function not differentiable at x equal to 1 when the one-sided derivatives are equal, and this is using rules. Because f of x was not continuous at x equal to 1, which then means that it can't be differentiable at x equal to 1. Let's see. Number 5. So these are just values you're putting in. If a function is not continuous and the function's derivative does not exist. Rule. That is a complete rule. Not continuous, not differentiable. What types of points are these? And I made a mistake in period 4. The first would be a removable, which you guys a lot of times call holes. The second, we forgot about, the jump. Number 3 would be the infinite, which most of you know as vertical asymptote. And the fourth is our oscillating. And that's the one that would be y equals sine of 1 over x was the example that I used in class. If a function is continuous, then the derivative sometimes doesn't exist. What are those types of points? So, a corner, the y value exists, but the derivative doesn't. A cusp, the y value exists, but the derivative doesn't, and a vertical tangent. And then the last piece, what are the 4 ways for a point to not be differentiable? You have to either be a discontinuity, and above are the 4 ways you have a discontinuity. You could be a corner, but that means you're continuous. You could be a cusp, that means you're continuous, and a vertical tangent, which means you're still continuous. All right? So for each of these functions, we're going to give what type of non-differentiable point and then find the x value. So I know based off of absolute values, the absolute value tells me there's a corner. Where is the corner? You would take what's inside of the absolute value. These are the transformations on the x. These are the 4 and the 5 are what make the x's go side to side, or the vertex go side to side, and actually shrink or stretch horizontally. So you take what's inside of the absolute value, set it equal to 0, and solve. So there is a corner at x equal to 5/4. This is actually the vertex of the absolute value function. Letter B, I know because it's an even over odd and the power is less than 1 that I have a cusp. I know that an odd over odd that's less than 1 would make a vertical tangent power. So take what's inside of the power and set that equal to 0, so I get that x is equal to positive 5. So there's a cusp at x equal to positive 5. Now the next two I did in class. Factor first. It should be screaming at you that it wants to be factored. And because these cancel, tells you that there's a removable, but problem, is that the removable at x equal to 3 can't happen because there's still an x equal to 3 left over. What that means is because it's left over and it's the bottom of the fraction, or the denominator, has to be a vertical asymptote, which tells me it's an infinite discontinuity. So, what type of point exists in part C? At x equal to 3, there's a discontinuity, which is an infinite discontinuity, and that's why it's not differentiable. The removable does not exist there. Whereas letter D, the factors would be x minus 3 and x plus 3. The denominator would be x minus 3 and then x plus 2. Because the x minus 3 cancels and it's not a leftover factor in the denominator, this tells me that x equal to 3 is a removable discontinuity, which means that it's not differentiable because it's a discontinuity. And then this one gives me that x equal to negative 2 is an infinite discontinuity, which then tells me, which means vertical asymptote, which then tells me also discontinuity. So, if I asked you for part D to find f primed of 3, you would get that it's undefined because the derivative doesn't exist. If I asked you to find f prime of 2, and you do your nice little quotient rule, and then you substitute in 2, when you're all said and done, you'd get an undefined. All right, bottom of the page. So what would the derivative graph of each x equal to a look like? And this should have been an a right here, a little bit confusing. So a corner. Let's remember that an actual corner looks like this. So there's my corner. What it looks like in terms of a derivative is that the slope is some positive value on the left side and then some negative value on the right side. So that was one example I think I showed in class, that it could be anything that has a jump discontinuity. Something like that, where the slopes are not the same value. Okay? A cusp, just to remember what a cusp looks like, kind of looks like that bird. So there's my cusp. Cusp will look like that the derivative from the left and right are opposite infinities. So the derivative from the left side of a cusp, this is negative infinity. The derivative from the right side of the cusp is a positive infinity. So you'll notice that it looks something like this. The vertical tangent, the graph of it looks like, and I'll do something like that. We'll put the cusp right, the vertical tangent right there. So that's the actual picture of the vertical tangent. A vertical tangent is where the derivatives both go to the same infinity. So for that picture, they're both going to negative infinity. So I'll actually make my graph match that. So this bottom part right here is where I'm graphing the function. But the top part right here is where I graph the derivative. And there is a huge difference, and I need to make sure that you understand the difference. The derivative doesn't exist at these points, which is why there's something odd happening at each of them. Here, you'll notice that at x equal to a, the y values exist. This is a continuous point. This is a continuous point, and this is a continuous point. I believe that's the end of page 2.